This is an introduction to the equations of motion, and the idea of the video is to show you how they are derived. So the equations of motion, often known as the Suvat equations or any other combination of those letters, are 5 equations that can be used to calculate the motion of an object. The S stands for displacement, the U stands for the initial velocity, V is the final velocity, A is the acceleration, and T is time. So these are the 5 equations of motion, and as you can see from them, they all have one letter missing. So the top one has no S, so no displacement. This equation has no use of acceleration. This equation doesn't use time. This equation doesn't use the final velocity, and this equation doesn't use the initial velocity. So let's look at where they all come from. So the idea of them is you only need 3 out of the 5 variables, and you can then calculate either of the other 2. So starting with V equals U plus AT, you can derive the 4 other equations of motion, or you can use basic ideas about speed, such as speed is distance over time. So if we look at this graph here, this is a velocity time graph where we have a constant acceleration. Now, in all of the Suvat equations, in all of the equations of motion, acceleration is a constant. The velocity goes from U to V. It accelerates over a time period t, and the gradient is defined as A. Gradient is the change in speed over time, or change in velocity over time. The final velocity is just the initial velocity plus any additional velocity, and the additional velocity will come from the acceleration times by the time, which gives you the increase in speed. The next equation comes from the same graph, and it's displacement. So because you can assume that if we do speed or velocity times by time, you have displacement, you can take that basic idea and use it, apply it to a velocity time graph, and when you do that, you find that the area under the line is the displacement. So the area of this particular graph here is the area of this part and the area of this part. Okay, now the average area, okay, or the area of the average speed multiplied by time gives you the displacement. So starting off from the basic equation of speed is displacement over time, if you take the average velocity rather than the speed and say that that's displacement over time, and you rearrange that equation by multiplying both sides of the equation by time, you get that displacement is the average velocity multiplied by the time. But we can see from the graph that the average velocity is half of the final velocity plus the initial velocity, just a simple basic mean velocity. So that equation then gives us displacement is half V plus U multiplied by T. And this next equation is going to be derived from looking at the area under the graph. So this uses the same idea that I was talking about just a second ago in the video. We can work out the displacement by taking the two components of the graph. So we have this component here and we have this component here. Now the area of this part of the graph is just the initial velocity multiplied by the time, so ut. So this part of the equation here comes from s equals ut. It's just saying this is the displacement caused by this part of the graph. This part of the graph here is a triangle, so you can use the area of a triangle. So the area of a triangle is half base times height, okay? Or half height times base. So the height of this part of the triangle is v minus u, multiplied by the base, then gives you t. But v minus u is the change in speed. The change in speed is the same as acceleration times by time, and so we can substitute at in for v minus u. Expanding that bracket will then give you s equals ut plus half at squared, and that's where that next equation comes from. There is another way that you can derive it, and we'll look at that later, but this is the easiest way. So that slightly harder way that I mentioned that we can use to look at the to work out that equation is via calculus. So if we start off with v equals u plus at, that initial starting equation, and we integrate it, the integral of velocity is displacement if we integrate with respect to time. And so the integral of at is half at squared, and the integral of the u section is just ut. So it's another way to do it, and if you're okay with calculus, it's nice to see that both methods work for this equation. This next equation, v squared equals u squared plus 2as, is a little bit more difficult to derive. There's just a couple of steps involved in it. But if we start with displacement is half initial velocity plus final velocity multiplied by time, then we can substitute in accordingly. So here's the substitutions. It's a lot of text all on the screen, but don't worry about it. If I lead you through it, s is equal to half v plus u multiplied by t. That was the starting point. Now, if we substitute v minus u over a equals t, this is just a rearranging of acceleration is change in speed divided by time. So acceleration and time have been swapped around. So if we substitute that in for time, then we get this equation here. If we then do a little bit of rearranging, if we move the 2 from the half to the other side of the equation, and the a, which are both being divided, then we get this 2as component. That leaves us with a simple set of double brackets, and if we expand those double brackets, you find that you get a minus vu and a plus vu, which cancel each other out. So, carrying on from there, we then just have 2as is equal to v squared minus u squared. The final equation then is just a simple swapping around to give us v squared is equal to u squared plus 2as. The next equation, very similar to s equals ut plus half at squared. It's essentially the same equation, only what you're doing is you're starting from vt and then you're subtracting an area of a triangle rather than adding an area of a triangle to ut. But if we do it algebraically rather than graphically, you have the starting point of s equals ut plus half at squared, and s is then, I can change the u here for v minus at. Okay, final velocity, take away acceleration times by time. And then I've just got this little equation here that needs to be tidied up. So I've got vt minus at squared plus half at squared, and the half will cancel out a half of this, and then you end up with the final equation here. And that's it. So if I go back, we now have the 5 equations of motion, all derived, nice and easy, and the next step is just using them. And the simple way to use them is look for the pieces of information given to you in a situation, and then decide which equation you need to use from which piece of information is irrelevant to the situation. So if, for example, you had a situation where time was irrelevant, you would simply use this equation, v squared is equal to u squared plus 2as, because it's the equation that doesn't have a time component in it. Thank you very much.